Hello, my dear friend. My name is Denis Volkhonsky. Welcome to the course Modern Deep Convolutional Neural Networks. Thank you very much for choosing this course. I'll do my best to share my knowledge in image processing with deep learning and convolutional neural networks with you. Let me begin with the motivation of learning convolutional neural networks. There exists a competition called ImageNet Large-Scale Visual Recognition Challenge. The task for the competitors is the following. You have 14 millions of images of size 256 to 256. Each image is assigned to one out of 1000 classes: cats, dogs, frogs, etc. You have to build a classifier, an algorithm that takes an image as an input and return the class of this image. This competition started in 2010 and the error on top 5 classes was 28%. Year after year, people develop neural networks that are deeper than previous, and in 2012 they consisted of 8 layers, then 19, then 22, and finally in 2015 people developed ResNet architecture, which showed the error of 3.5%, and what is amazing about it, it outperformed human. There are several reasons for it. First, the network is really big, 152 layers. In fact, learning of such a deep network not only long but also very hard. And authors proposed how to overcome such limitations, which we, sure enough, will discuss in our course. The second reason, this network is able to recognize such classes that many humans can't recognize. For example, this network can distinguish different breeds of dogs, and I'm not sure that all of you can distinguish between these two different breeds of dogs on the slide, but they are different. Neural networks show amazing performance in many tasks. In 2013, Kaggle, the biggest machine learning competition platform, hosted a Dogs with Cat challenge. The task was to classify whether there is a cat or a dog on the photo, and the accuracy of the winner's model was almost 99%. During our course, we will move from the basics of convolutional neural networks to the recently developed advanced techniques for training them and achieving the highest score. Firstly, we will consider which problems can be solved with convolutional neural networks. We will briefly remember linear layer and how to train multi-layer perceptron, what is loss function and how gradient descent works. We will study convolutional neural networks, what it is, how to use it, what are the parameters, etc. Later, we will move forward to studying advanced deep learning techniques such as batch normalization, instance normalization, and others. I will tell you the most modern regularization techniques such as dropout, drop connect, and others. We will learn what is an autoencoder and how to apply it in practical business tasks. Finally, we will study the most popular convolutional models for classification tasks and study how to use them in order to solve problems with a small amount of data. Thank you and see you in the next video. Let us now consider the hottest topics of research in computer vision. All of these problems are solved using convolutional neural networks. Each of the problems is a separate topic, and in this course I will pay attention on the basis for all of them, convolutions and training of neural networks. The first basic problem in computer vision is classification. Usually you have to build a function that takes some image as an input and produce a label for this image. On the slide you can see a simple case of classification, binary or two-class problem. Our neural network should decide whether there is a cat or a dog on the image. Second computer vision problem is image segmentation. For the given scene image, we should find where each object is located and mark pixels of different objects with different colors or classes. For example, on the slide, the glass is marked with a blue color, the laptop is black and the table is yellow. Usually, this task is solved with the classification of each pixel separately. Another example of computer vision task is object detection. For the input image, we need to find all the objects in the image and highlight them with a rectangle, which is called the bounding box. The next problem of computer vision is image captioning. For a given image, the model should generate a text description of this image. As there is in the slide, for the input image, the caption may be "the man is passing the road." The problem of person identification is widely used in the bank system. Usually banks would like to identify persons by the photo and say whether this is the same person or not. We will study this problem at the end of the course. In 2014, Goodfellow proposed a new method of generating synthetic objects, generative adversarial networks. They are able to learn the trained data distribution and sample from this distribution. Now, generative adversarial networks can generate synthetic objects of big size and high quality. Another recently proposed method can transfer styles of great artists to a photo. The input photo is on the left corner and other three photos are stylized with different styles of famous drawings. Thank you for watching and see you in the next video. Now I'm going to remind you the core classification and regression pipeline. I will briefly describe what is loss function, how to build a multi-layer perceptron and train it. You can skip this video if you think you are good at these topics. Let's start with the linear layer recap. This in fact is a basis for every linear classifier, such as logistic regression or SVM as far as for linear regression. Many people like to explain linear layer using neurons, which for me seems very complicated. I like to look at linear layer as the linear transformation from one linear space to another. So we have some input vector x from the n-dimensional space. Linear layer, or if you like, the linear transformation, is defined by the transformation matrix of size n to k. In terms of neural networks, this is a weight matrix which is updated during training. In PyTorch, this is called linear layer, n is in features and k is out features. The transformation itself is a matrix multiplication of the input vector and weight matrix. After matrix multiplication, we need a new vector of size k, and in fact this is all about the linear layer. We can stack several linear layers into one neural network. Don't forget that combination of linear transformations is also a linear transformation. That's why you should always insert nonlinearity between them, for example sigmoid function. The sigmoid is a bad choice, but don't worry, we will study which nonlinearities to use later in this course. Depending on the problem, we consider the different number of output neurons. In the case of classification to k classes, we should have k output neurons and use cross-entropy loss with softmax layer. In case of regression problem, we should use one output neuron with any regression loss function, for example L2 Euclidean distance between predicted and target values. Now let's talk about classification. In this section I will describe the full classification pipeline. We have some input vector. Each element of the input vector is a feature. This vector is a part of a linear space. We can apply a linear transformation to it. This is called linear layer. As I said before, the linear layer is represented as a matrix of learnable parameters. Then we apply some nonlinearity such as sigmoid or hyperbolic tangent. If we don't, we will get the problem. From linear algebra, we should remember that combination of linear functions is also a linear function. Thus, adding several layers, one after another, will lead to some bad effects during training. Now we can repeat this action several times in order to make our network deeper. Between each linear layer, we add nonlinearity, such as sigmoid or hyperbolic tangent. If we want to perform a classification to C classes, then we need to set C as an output dimension of our network. The last layer is now called logits. It consists of numbers from -infinity to infinity. Each logit is responsible for one class. The more the logit, the higher the probability of the corresponding class. Usually, we should transform our logits to probabilities. Here is softmax layer comes to help us. Probabilities that we obtained on the last layer can be used in two ways. First, prediction. Second, training, where we use the probabilities for computing the loss value. The less our loss, the better our predictions are. If loss is computed, we can minimize it using stochastic gradient descent algorithm. Minimizing the loss is the process of training neural network. To predict the class for the input object, we use the class with the highest probability. And that's it. Thank you for watching and see you in the next video. Let us talk about softmax layer and loss functions in details. The first thing we are going to consider is a softmax layer. This layer is widely used in classification and it's just transforming logits to probabilities. You can look at it as a normalization. Firstly, we transform all logits with the exponential function. And secondly, we divide by the sum of the exponent for all logits. Please stop the video here and think, why do we need both two transformations? Exponent for all the logits and normalization. And why we call the output of this layer as probabilities. Let us look at an example of softmax layer. We want to classify to 4 classes: cats, dogs, cow and horse. The output of the last layer of the network is 4 logits: 4, 1, 2 and -8. Softmax layer allows using each of these logits for normalizing them to probabilities, which are on the right. While probabilities are computed, it is important to speak about the loss function. Now we are talking about the binary version of cross entropy. Let's look at it in details. The first thing we see is W, which is the weight of the current object. The loss function is computed for each object and then we average it. Thus we can compute not usual average, but weighted one. However, usually all weights are equal to 1. After setting some weights to the object, we have the target value for our object. Since we consider the binary classification case, our labels take values either 0 or 1. Depending on it, we will have only one non-zero term, left or right. We also have the predicted probability of class 1, which is the output of the last layer of our neural network with sigmoid function at the end. Since it is a probability, it takes value in range from 0 to 1. If our target label is 1, then we have the only left term and maximize the probability of class 1. If the target label is 0, then we minimize the probability of class 1. Note that maximizing or minimizing is regularized with the minus before the loss. Let's consider the full cross-entropy loss function. In PyTorch, it is called cross-entropy loss. What you should know about it is that we maximize the probability of true class and minimize all other probabilities. If you use cross-entropy loss in PyTorch, note that it already includes softmax layer inside. Considering regression problem, you are free to use any regression loss, such as L2 Euclidean distance, L1 Euclidean distance, or any other. Just to remind, you should compute average distance between your predicted y and target y. The more the distance, the worse your predictions. Thank you and see you in the next video. Now I'm going to briefly remind you the stochastic gradient descent algorithm, the common way to train deep neural networks. Gradient descent is an algorithm that step by step updates the parameters of the network going to the minimum of the loss function. Starting from some initial parameters, we move in the direction opposite to the gradient vector. We have a loss function L of x and the theta that we wish to optimize. In other words, we want to find such parameters theta that minimize the loss function. We set up some initial parameters theta 0. In this course, we will later discuss how to properly choose the initial parameters of the neural networks. Here is the formula for gradient descent algorithm. Let's look deeper into it. Firstly, we compute average loss. The loss function is computed for each trained sample and averaged. Secondly, we take its gradient according to each parameter of the neural network. In this formula, we consider the update of the ith parameter. Then we should multiply our computed gradient on the predefined learning rate, which is the speed of learning. Next, we update our parameters by subtracting the gradient multiplied by learning rate from parameters from the previous step. Since we live in the era of big data, computing the average of loss function on millions or billions of objects seems computationally impossible. However, we can use not all the data from our training dataset, but just the subset of it. This is what people usually call stochastic gradient descent. You should understand some facts about the choice of the batch size. The more your batch size, the more GPU memory is required by your neural network. Therefore, you are bounded above in the choice of the batch size. On the other hand, it is better to take a bigger batch size, since it will decrease the variance of your gradient. The low values of batch size will lead to high variance. The third important note: prefer to take the batch size which is a power of 2. The reason for this is the binary system in the lower level computations. It will be just faster. The usual choice 32, 64, 128, and so on. The last but not the least, for stochastic gradient descent and its modifications, it almost doesn't matter how big is your batch. What is important, the number of updates. It will be almost no difference between batch size 256 and 512, since you just slightly improve the estimation of the average gradient. Let us now consider how we work with data in the mini-batch setting. As usual, we have a set of training data. At each iteration of neural network, look at the batch of data points. When the neural network looked at all the data, it is called the epoch. We're now going deeper into details. The first thing you should do is shuffling your data before each epoch. We fix the size of the batch to some value and split all the training dataset into batches of this size. We update our network according to the gradient computed with the first batch. Then second batch. We update our network batch by batch. Note that the last batch has size that is smaller or equal to the batch size because the total number of training samples is not obliged to divide by the batch size. All I showed you is called an epoch. After it, we start next epoch of training. Note that we should shuffle our data again. There exist a number of modifications of stochastic gradient descent, which use some empirical improvements of the convergence. But this is not the topic for our course. In practice, it is always better to use Adam algorithm for neural network training. Adam is also the modification of the stochastic gradient descent and is available in PyTorch. That is all for now, and thank you for watching. See you in the next video. Hello, my dear friend. Welcome to the practical part of modern deep convolutional neural networks with PyTorch. In this video, we'll build a linear classifier for the dataset which is called CIFAR10, which consists of 10 classes of images, like plane, car, bird, cat, deer, etc. So first, let's look everything we need. This is PyTorch, Matplotlib, and NumPy libraries. In the next cell, we have the following code. First, we define the transformation that will apply to all our images. What it is? First is transformation from the NumPy array to the tensor. This tensor is the basic element of PyTorch library. The same tensor we can see in TensorFlow or in Theano or any other library. Second thing is normalization. If we look at the signature of normalize class from the transforms, it says that we will subtract this mean, that is 0.5, 0.5, 0.5, and divide by its standard deviation, which is again 0.5, 0.5, 0.5. So this is what we will obtain. And since our images have values from 0 to 1, then after this normalization, our images will be centered by subtracting this mean, and will have standard deviation equal to 1. So they will be normalized. And this is very good practice before training every neural network. After that, after we define the normalization and the transformation that will apply to all image, we should load our dataset. For this purpose, PyTorch have very good tools which is called dataset and data loader. So what we do here, first we load the dataset, and you see its name, it's CIFAR10. We say that it will be located in the data folder. We say that we want train set, not test set in this section. We should download it because we don't have it. And we want to apply the transformation that we defined. After we define the train set, we should write a loader. Loader is a class in PyTorch that says what will be the batch size, do we need to shuffle our data, how many processes we should use for loading this data from the memory, and so on. So we'll use batch size, which is equal to 4. We'll shuffle all our data, and we'll have 2 processes to be workers and to load our data from our memory. We do the same with train set. The difference is now we have train equal to false. So let's apply it. Finally, in this cell, we define classes that we have: plane, car, bird, etc. Totally there are 10 classes. So now you can see that we are waiting until PyTorch will download all the necessary files, unpack them, and so on. So as you see, files already downloaded and verified. Good. Now let's normalize this data. Let's do it. So we get some random train samples, which is 4 because we have batch size 4, as I said before. And we use very good tool for making grid of images, which is called PyGrid in Torch Vision library. And here you can see images. They all have size 32 to 32 and have 3 channels: red, green, and blue. Okay, so you can see plane, horse, bird, and bird. We in fact can repeat this action and obtain another 4 images. Now we have to write some linear classifier in PyTorch. For this, we need to define a class which we call linear classifier. here you can see an n.module, and we want that it will obtain n input neurons and return n output neurons. A bit later I will describe what is n input neurons and n output neurons. So we have to define our linear classifier. Linear classifier consists of one layer, and this is linear. This is called linear. So nn.linear. nn is torch.nn. And here we say n input neurons and n output neurons. How many neurons I will describe later, as I said. Okay, this is our linear layer. We should add self.linear in order to make a call of this class in forward function. So now, in order to complete this neural network, we should define forward pass. We don't need to define any backward pass because PyTorch will automatically do backward pass for us. So in forward pass we do the following. We want to apply self.linear from x, and we should return it. Okay, will it work? And I say no, because image x have shape, batch size 3, height, width. That's why we can't apply linear layer, because it's an image, and what we need to do is to reshape this x to the batch of vectors. And how we can do it? We should define the variable batch size, which is equal x.shape0. Then we say that x is equal to x.view, which is equivalent of reshape in NumPy, and here we have batch size and -1, which will mean that first dimension will be batch size and second dimension will be 3.height.width. And good, this is it, and we defined our neural network. Now we have to define this class, so linear classifier, and it takes some n input neurons as a parameters and n output neurons. N input neurons is equal to something, and n output neurons is again equal to something. Okay, what should we do here? Here we should say that it will be 3.height, height dot width, because here we multiply, we have a product of these shapes here because of -1. That's why the dimension of our input space will be 3.height.width. Okay, what is height and width? Let's check the size of our image. We have here images, let's say images.shape, and look, it is 4, 3, 32, 32. So this is batch size, this is number of channels, and this is height, this is width. Okay, so we can see that height width is equal to images.shape from second. Okay, and let's check that it will be 32 to 32. Yes, we're right. Height and width is equal to 32. And how many neurons we should have in our output? And I say to you that it should be exactly 10. Why 10? Because we have exactly 10 number of classes. And when making a forward pass, we should obtain one score for each class. And this score will, with softmax layer, is translated to probabilities. And again, we should have 10 probabilities because of 10 classes. So this is our call of our class. Not call, this is the creation of object from our class. And then we apply .CUDA, which means that we should transfer our network to GPU. Now we have to define the criterion, which will be cross-entropy loss, which I mentioned on the lectures. And we use optimizer, which is Adam, which is now state-of-art and the best optimizer that were invented and is good for deep neural networks. We pass it the parameters of our network, and we set the learning rate to some value, which is 0.01. Now we have a loop for training. What we have here? We have 5 epochs. Epoch is that I described you in the lecture. So we want to look at each image from our dataset 5 times. Now, at each epoch, we use our train loader that we defined at the beginning here, train loader and test loader. And as I said, it is very convenient that we can do the following. So we just say for data in train loader, and that it is. So each our data is input and labels. We translate these input images. Sorry, this should be images. Images as an input and labels is our data. We translate these images and labels to GPU for speeding up training. After that, in PyTorch, we should make our gradient to 0. Here we should make forward pass and compute loss. So how to do forward pass? We just need to apply our network to images. And this will be our output. And in order to compute loss function, we need to say that loss is equal to criterion from output and labels. And this is it. Just 2 lines of code. And after that, we make backward pass, we make optimization step, and this is just debug printing. Let's run this. Okay, our training now was finished, and you can see how the loss decreased from 2.3 to 2.28. And now let's check the result. For this purpose, we will use test loader in the same way that we use train loader in training, which is here. The difference that we don't use any gradients or backward pass, and that's why we write torch.noGrad here. What we do is just make forward pass calling our net class, and after that we use torch.max function in order to obtain the class with the maximum score. And let's compute the accuracy. So we have the accuracy is equal to 31%. It is not random, it is better than random, because random classifier will have 10% accuracy because we have 10 classes. This is 31, this is better than random, but again, this is just linear classifier. In next video, we'll consider multi-layer perceptron, and then we'll move forward to convolutional neural networks. Thank you, and see you in the next video. Now let us modify the linear classifier that we built in the previous several videos into multi-layer perceptron. The difference between the multi-layer perceptron and the linear classifier is that now we have not one linear layer, but a set of linear layers and some non-linearities between them. So we take the same code for data preprocessing, such as import data, PyTorch says that we already downloaded and verified all files. Then we can again visualize our data set, which is, remind you, is CFAR 10, which consists of 10 classes of images of size 32 through 32, which has 3 channels each. Then now we have a linear classifier that we built on the previous videos. Now let's rename it to the multi-layer perceptron and let's modify it. So as I said, we have several linear layers. Okay, let's do the following. Let's say that now we will have what is called main sequential block. Sequential is a nice tool in PyTorch that allows to write several layers as a sequence. So the first layer will be an n.linear, which has n input neurons and let's say 256. Then second linear layer will be an n.linear, and now we have the input neurons 256 and output, let's say, 128. The third linear layer will be our last one, and it will have 128 input neurons and 10 output neurons. No, not 10 and output neurons. Here, yes. We delete these, and instead of self.linear, we just call self.main. And that's all. So now, please stop the video and think, where is the mistake that I made? I hope that you guessed that, as I said in lectures, it is very important to insert some nonlinearities between linear layers, because the combination of linear transformations in the linear space is again a linear transformation. It is the first reason, and the second reason we can obtain some bad effects with gradients if we have several linear layers one after another without nonlinearities. So just let us insert leaky relu here. And as far as I remember, we should say that in place should be true. And let's insert the same layer here. Okay, and if you see the parameters, here is negative slope, which is now 0.01. We can set it to, say, 0.2. 0.2. This is a hyperparameter, and of course we usually should tune it with some validation set. Okay, so we are done. Then again remind you, we obtain height and width of our image. Then we create not linear classifier but MLP, multi-layer perceptron. Again, input neurons is 3.height.width and output is 10. And set it to CUDA. Good, we created our network. Then again, criterion and optimization algorithm. And again, we have 5 epochs of training. And let's train our network. Good, our training was finished. Let's obtain test quality using the same function that we used for linear classifier. So, and now we have 45% of accuracy. In linear classification, we obtained 32% of accuracy. Now we have 45, when the random classification will give us 10% accuracy. Okay, that's not very good result, of course, because we don't use convolutional layers at all, and we don't tune the network. We just take some random layers, but we again improve the results. In the next section, we'll consider convolutional layers and will significantly improve their results. So continue watching, thank you, and see you in the next video. In this video, I'm going to describe what is image and what people did before deep learning. Usually, gray image is represented as a matrix of size height to width. In this matrix, there are pixel values which could take values from the range from 0 to 255. Another way to represent an image is matrix of pixels that takes values between 0 and 1. If we are talking about color images, usually it is represented as a 3D matrix of size 3 to height to width. Each pixel now is represented as 3 values: red intensity, green intensity, and blue intensity. These is so-called channels of the image. Let us consider old-school approach for image processing. We, as always, start from data. Usually this is a set of images. For each image, people constructed a set of features by hand. Using obtained features, one can use any standard machine learning algorithm such as linear regression, SVM, gradient boosting, or any others. Considering images, people used to construct so-called image descriptors. These descriptors were not learnable at all. As you can guess, the choice of the descriptors influenced training and prediction results a lot. However, now it is the area of deep learning, and the key advantage of the deep learning approach is automatic feature learning. With neural networks, you don't need to think about features and descriptors. You construct a neural network and it learns all features for you. Thank you for watching. See you in the next video. In this course, we study convolutional neural networks. However, we should understand why we have to use them, why not to use just linear layers. Quite an obvious question. Why not to use linear layers with images? After all, we can just reshape our image to vector and do a forward pass through a set of linear layers with non-linearities. Good idea, but if our input image has 3 channels and size 256 to 256, after reshaping we will have a vector of size around 200,000. That's the main motivation for introducing convolutional neural networks. Too much parameters in the linear layer. Before we start learning convolutions, let us consider some assumptions. Could you agree with me that the closed pixels have closed values? Actually, if we consider the pixel on the cat, which is red, with high probability closed pixels will be also red. Okay, so we don't need a separate neuron for each pixel. The open question for now: how we can reuse the parameters of our network? If we don't need a separate neuron for each separate pixel, we should use one small linear layer for local regions of the image, and this is a basic idea behind convolution. We understood why we should use convolutions instead of linear layers for images. Let us now consider convolutions in details. Let us look at the visual explanation of the convolution. Again, we have an input image of size C to H to W, where C in the number of channels, H and W is height and width correspondingly. We introduce convolutions weight, 3-dimensional matrix of size C to K. Here it is. The number of channels is the same in the input image and in the weight matrix and equals to C. We use convolution weight for sliding over the image, taking the element-wise product of the local region of the image, which is green, and the weight 3-dimensional matrix, which is blue. We sum up the result of the product and obtain one value. We write it to one of the values of the output 3-dimensional matrix. We repeat this action several times with different filters: yellow, red. In fact, convolutional operation consists of several kernels. Convolutions were popular before deep neural networks and was called filters. On the slide you can see the result of applied Gaussian filter to an image. You can see that depending on the parameter of this filter, the image lost its color and became blue. Convolution is an operation which can be represented as a layer in a neural network. That is why you can combine several convolutional layers into one neural network. Let me demonstrate the main advantage of convolutions against linear layers. Assume we have an input image with 3 channels of size 256 to 256. We want to obtain 100 output features after the first layer. Then, using linear layer, we will obtain 19 millions of parameters. In the same time, 4 convolutional kernels will have only 300 parameters. Now you see the difference. In the next video we will go deeper into convolutions. Thank you for watching. Convolution operation has several parameters. Let's discuss the most important: stride and padding. The first parameter of the convolution is its stride. The default value of the stride is 1, which means that our kernel is moving from left to right and from top to bottom by 1 pixel. On the animation on the slide you can see how the convolution with stride 1 works. In the animation, the red is a kernel, the green is the input image. Note that if we have input size 4 to 4, kernel size 2 to 2, then the output size will be 3 to 3. Now let's increase the stride to 2. Look what now happens. We increased the stride and the size of the output of the convolution decreased. Now it is 2 to 2. That is why on the first layers of the network it is better to use stride more than 1 in order to downsample input images. Okay, now let's set the stride to 3. What will happen? Probably in this case PyTorch will return an error. This is because the size of the image, which is 4, can be divided to the size of the kernel, which is 3. I hope you understood what is stride, so now let's switch to another parameter, padding. Look at the image on the left. If we apply convolutional layer to it, we will obtain an equal contribution of pixels to the result of the convolution. Green pixels will play their role more than blue pixels. If we want to make the contribution of pixels equal, we could add zeros on the border of the image. And here you can see how it looks like. Red pixels have now value 0. Another reason for the padding is that we consider on the previous slide. If our image size is not divided by the kernel, we can always extend the image with 0 padding. Another possible variation of padding is mirror padding, which is in the PyTorch is called reflection padding. In this case we add not 0 pixels, but we reflect the border pixels as it is on the slide. Well, this is all for padding. Thank you for watching and see you in the next video. The convolution operation is a linear function in the linear space. It means that between several convolutions it is important to insert nonlinearity function. Let's look at the most popular choices and discuss their advantages and disadvantages. The most popular nonlinearity are sigmoid and hyperbolic tangent. The sigmoid transforms the input to the value from 0 to 1, while hyperbolic tangent transforms an input to the value from -1 to 1. Both hyperbolic tangent and sigmoid are bad choices. Let's look at sigmoid's gradient. It is equal to 0 almost for all inputs. It has its largest value in the point 0. The value is 0.25. It means that for most of inputs, neural network weight will not be updated at all. The same situation is with hyperbolic tangent. Another popular choice of nonlinearity is ReLU function. It sets the input to 0 if it is negative. It is maximum from 0 and x. However, it sets the derivative to 0 in the half of the inputs. If the input is negative, then the derivative will be 0. Again, it means that your weight will not be updated. One rather nice modification of ReLU is leaky ReLU. It doesn't set the negative input to 0, but slightly change the slope of the negative input, as you can see on the slide. It is a good choice in most of cases. There are much more nonlinearities exists in every deep learning library. Usually, in practice, the best choices will be leaky ReLU and ReLU. However, you may use some validation set of samples in order to choose the best nonlinearity. Thank you for watching and see you in the next video. In this video, I will show you the most popular ways of downsampling images. Sometimes we have a very big images as an input. For example, the size can be more than 1000 pixels. If we will process it directly, we will need a lot of parameters in the network. However, in order to recognize if it is a cat or a dog on the image, we don't need so much information, we don't need so many pixels. That is why our goal is to reduce the input image size. For this purpose, people usually use max pooling layer. It divides your image into squares of some fixed predefined size, and in each of the square it selects maximum value. As in the example on the right, in green square it selects 6, in red square 8, in blue 3 and in yellow 4. In the example, the size of the square is 2 by 2. In the max pool layer, we have the same parameters as in convolutional layer. Kernel size, which is the size of the squares, also stride, the same as in convolution, and padding, also the same as in convolution. Another type of pooling for images is average pooling. The only difference from the max pooling is that now we leave not the maximum value, but an average one. You may ask me, Dennis, so what should I use, max pooling or average pooling? Who knows, I will answer to you. In practice, there is not so much difference between these two methods. Often people prefer to use max pooling instead of average pooling. Thank you for watching and see you in the next video. Now let's discuss how to build deep neural network. As I already mentioned, it is important to add nonlinearity between each convolutional layer, because convolution is a linear operation. Usually, after a set of convolutional layers, we reshape the obtained output to be a vector. Then we add several linear layers with nonlinearities between them. As a result, we should obtain a vector of size that is equal to the number of classes in the classification problem. If we solve a regression problem, then the output size should be 1. In order to build deep network, we should stack several blocks that contains convolution with nonlinearity. After that, add max pooling layer. We can repeat this big block several times. After that, we reshape the output vector, use linear layers with softmax at the end. Now, this is our deep convolutional neural network. Thank you for watching and see you in the next video. We have already built a linear classifier and multi-layer perceptron for classification of CIFAR 10. Now let's switch to convolutional neural networks. So let me restart the kernel and clear all outputs. Now, we again import all necessary libraries. We again load our data, which is already downloaded and verified. We again have train set, test set, train loader and test loader. We can look at our images. Again, we have 10 classes. All of them have size 32 to 32 and have 3 channels. Now, we have to build a convnet. From the lecture, you should remember that when we build a convnet, Usually we start from the set of convolutional layers, and after that we use several multi-layer perceptrons. Okay, so in PyTorch we have two parts. I wrote two parts here. Main part, which is convolutional part, and MLP, which is multi-layer perceptron, which stands for set of linear layers. And when we will do forward pass, we will apply first convolutional part, then we will reshape our output to the batch of vectors, and then we will apply multi-layer perceptron. Okay, now I will show you the service which is called Fomora AI, which is very helpful when you build a ConvNet. It is good when you want to understand what will be the output size of your convolutional neural network. So what we have here? We have the input size 32. It means that our images is 32 by 32. Then we should define a convolutional layer. Here is kernel size, stride, dilation, and padding. We didn't discuss dilation yet, but other parameters I assume that you know. Okay, let's set the kernel size to 5, for example, the stride to 2, and the padding is valid. We have two options here, valid and same. So let's look. When we use same padding, it means that all pixels will have the same contribution. This is what I described in padding video. If we use valid padding, then our padding will be 0. It means that no padding will be applied. Okay, so what we have here? Layer 1, kernel size 5, means the kernel is 5 to 5. The stride is 2, padding is 0, input size is 32, and the output size will be 14. It means that the output will have shape 14 to 14, and we will have several channels. But there is no any word here about channels because this is not important here. Okay, we can duplicate this layer and apply it after the first one. So the input size will be 14 now, and the output size will be 5. And for example, if we want to duplicate it, then we will obtain the input size 5 and the output size is 1. Okay, so we can use 3 layers which has the same parameters: kernel size 5, stride 2, and padding 0. Let's write them. nn.conv2d. Then we have parameters in channels, which is n channels, and next parameter is out channels. Out channels is the number of filters which we will have in our convolutional layer. Let's say it will be 16. This is a hyperparameter. Of course, it should be tuned with validation set. Now we have kernel size. Kernel size, we decided to set it to 5. Then stride 2, then padding 0. Okay, and that's all. Now we should repeat this layer 3 times. But here we have now not n channels, which is 3 in the input, but now it will be 16. And let's say the second layer will have 32 filters. It means that the third layer will have 32 channels as input, and assume it will have 64 kernels. Now, this is our convolutional part. As I said you in lectures, convolution is a linear operation. It means that between each convolutional layer we should add some nonlinearity, because the combination of linear layers of linear transformations is the same linear transformation. and we can obtain again bad effects with the gradients of the network. That's why we can write here like relu and in place true here and here. Good. So now we have the main module, which consists of 3 convolutional and 2 nonlinearities. After it, we can also apply some relu layer. Here, after applying main, we will have the shape, X shape, batch size 64, because we have 64 output channels, 64 kernels in the last convolutional layer. Then 1 to 1. Why 1? Because after applying 3 convolutional layers, the output size is 1. So 14, 5, and 1. Now we have to reshape this like image consists of 1 pixel and 64 channels. We should reshape it to the batch of vectors. Again, we use x.view batch size -1. And after that, we apply multi-layer perceptron. Okay, let's write it. And then .linear we'll have 64 input neurons, input elements, and the output dimension that will be 32. Then nonlinearity, let's say it will be relu in place true, then again and then dot linear 32 to n output neurons. And output neurons for our task will be 10, because we have exactly 10 classes. So let's compute height and width, and as it was in the previous lectures. And now n channels. N channels is 3, because if we look at the image.shape, it is 4 to batch size and 3 is the number of channels. So number of channels is 3. And output neurons will be 10. It means that we need to classify to 10 classes. So again, let's create our convnet, send it to CUDA, and check that if we apply our network to some images, it will have the output size 4 to 10. 4 stands to batch size and 10 stands to number of classes. Again, we have some criterion, which is cross entropy loss. We have Adam optimizer, and let's run our network for 5 epochs. Okay, our training was finished, and now let's check the quality. So now we have 59%. If you remember, when we trained multi-layer perceptron, we had 45%. So we improved our score. In the next practical videos, we'll improve our score more and more, applying on practice what we learned in lectures. Thank you for watching, and see you in the next video. If you studied machine learning before, you should know what is overfitting. Also, you should know how to avoid overfitting and what is regularization. However, there are a number of regularization techniques that are good for deep learning and image processing. From the course of machine learning, you should know that when you increase the number of parameters in your model, it starts to overfit. The overfitting means that your model learns the answers for the training objects instead of predicting them. This leads to bad behavior of your model on the test set. The prediction will be very bad. The solution to the problem of the overfitting is the regularization. Stop. You may ask me, why should we regularize the network? Maybe it is better not to increase the model size? So, we have two possible approaches. Deeper network with regularization or smaller network without regularization. Let's think. Our last function is non-convex. It means that there are multiple local minimums of the last function. But the local minimum is usually good for us. Yes, it is better to reach the global optimum, but now optimization methods for deep learning can't do that. If we have small number of parameters, then we have a few local minimums. And in practice, they are bad. If we increase the number of parameters, making our network bigger, then our loss function will have more local minimums. And usually, in practice, it is better. The conclusion is simple. It is better to have a deeper network with regularization than small network without it. Of course, you should understand that this is practical results, and in your concrete case, the situation may be different. The first method of regularization comes from the classical machine learning, L2 regularization. The idea of it is the same as in ridge regression, which is a name of linear regression with L2 regularization. We have some loss function for our neural network, and we add the regularization term to the optimization problem. This regularization term consists of the multiplication of lambda to weight. Lambda is the regularization coefficient which should be tuned on validation set. The more lambda parameter, the closer our weight will be to 0. In order to implement such regularization in PyTorch, you can use the parameter weight decay in the optimization algorithm definition. This is absolutely the same parameter as lambda in our formula. We considered the L2 regularization, but there are much more regularization techniques that were designed specifically for deep learning. The first deep learning regularization technique is dropout. It is easy to understand it on the multilayer perceptron. On the left, we have the original multilayer perceptron with several layers. On the right, we have the same network but with applied dropout. Look, we turned off some of the neurons. In other words, we made some of the input feature to be equal to 0. And the important thing, we did it randomly. Let's take a closer look. We at first set some probability p of the input feature to become 0. Now we have two cases, training and testing. During training, we set some features to 0 with the probability p. On each forward pass, that is, on each iteration, we choose different features. We can look at it another way. We generate the Bernoulli mask and multiply it to the features. During testing, as we sampled the mask from the Bernoulli distribution, we should take the average. So we multiply our input features to the probability p. Dropout is usually implemented as a separate layer, which randomly sets some features to 0. That is why it is possible to add dropout multiple times before the layer you need. By default, the probability in the dropout layer is set to 0.5. However, it can, and in fact should, be tuned on the validation set. Also, there exist some research papers that describes the way of automatically choosing the separate probability p for each feature. If you are interested in it, read about the variational dropout. Dropout can be used as a good regularization technique. But what if you want to train an ensemble of neural networks? As you may know from the machine learning course, ensembles of predictions, for example gradient boosting or random forest, always works better than the single algorithm. for example decision tree. Constructing an ensemble of neural networks is hard. It will require a lot of computational time and memory. However, dropout comes to help here. Since for each forward pass during training we sample a random Bernoulli mask, we have a new neural network on each iteration. That is different from the previous one. And we can use these different networks as an ensemble, for example, averaging their predictions. And good news is that we don't need to store them separately. We just put the same data to the network input, each time randomly making some inputs for some layers to 0. Authors of the cited article showed that such a dropout ensemble usually works better in terms of prediction quality. The other regularization technique is drop connect, which is also can be used in deep learning. It is very similar to dropout, but with a bit difference. While dropout sets some features to 0, drop connect sets some weights to 0. The pipeline is the same as in dropout. We choose some probability of the weights to become 0. During training, we set the weights to 0 according to the selected probability. During test time, we multiply our weight on the probability p. Here is the comparison of dropout and drop connect methods. Although the difference between them not that much, people prefer to use dropout. Since we study modern deep image processing, I have to share with you recently proposed regularization technique for images, drop block. The intuitive idea behind dropout is that we sometimes should set some pixels to 0. But we know that usually on the image there are only a limited set of pixels that contains useful semantic information. For example, for the dog photo, useful region is green on the middle image. If we learn a classifier with 2 classes, cats or dogs, then we don't need the information that surrounds the dog, which is in this photo the grass. The disadvantage of the dropout as a regularization technique is the following. If we set pixels of the grass to 0, then it will not affect the prediction results at all, since the grass is useless information. In other words, sometimes our regularization will not work, because we want our regularization method to debrief our network for solve semantically important information during training. Only it will help it in preventing learning the training samples. And here comes the drop block algorithm. On each training iteration, it set the random square of pixels to 0, as it's shown on the right image. You can think of it in the following way. If our network could recognize the dog on the photo, it is also should be able to recognize a dog without an ear or without a mouth. And this is the idea behind drop block. How it should be implemented? In fact, rather simple. At first, we set the length of the side of a square, which is called block size. We also should set the probability of the block with the central at each pixel to become 0. Then, knowing the block size, we can select a region which potentially can contain the center of the block. Of course, we can't store the center of the block to the corner of the image. This region is green on the left image. Here we have the block size equal to 5. After that, we generate a Bernoulli mask of size that is equal to the green area. For the Bernoulli mask, we use the probability that we set up before. As you see on the left image, the Bernoulli mask gave us 2 centers of block to make 0. And on the right image you can see the result of the drop block. Some pixels became 0. As in the dropout, the drop block is random on each iteration and don't play his role during testing. If you want, you can read the original paper by the link in the right corner on the slide. The experimental section of the drop block paper shows that these regularization techniques allows modern architectures such as ResNet-50, which we'll study later in this course, to overcome the same architecture with dropout in classification accuracy. Here is another interesting visualization from the authors of this paper, class activation mapping. At the first row, there are input images, and other three rows, original model, model with a drop block with block size 1 and with block size 7. Model, when trained with drop block, learns spatially distributed representations that induce high class activations on multiple regions. On the other hand, the model with drop block tends to focus on one or few regions. So here it is all for drop block. If you are interested, please read the original paper. Another important regularization technique is early stopping. We already considered several regularization techniques such as L2, dropout, drop block, and others. But the open question is, can we just stop our learning earlier? And the answer is yes, we can, and in fact we have to. Usually, when you train your neural network, you plot two metrics. Some loss function on your train set and test set. It may be the loss that you minimize or the accuracy of the classification or any other. And while training, you train, error should always decrease and your test error decrease only some limited time and after that starts increasing. This is what is called the learning curve, and I hope you studied it in machine learning course. In order to stop earlier, you should define where to stop your model. The stop may be somewhere as on the slide, or the stop may be here sometime later. So the question is where to stop. And here comes the early stopping algorithm. It is important to say that since we use batch gradient descent, at each iteration our loss can decrease or increase. This is normal thing that you will always see while training. That is why we need to introduce parameter n steps. It means how many steps should we be tolerant to validation loss increasing. In other words, how many iterations should we wait while the loss is not decreasing. Let us look at the algorithm implementation in Python. At each iteration, we check if our validation loss decreases comparing to last n steps. Of course, if you consider accuracy, it should increase. So if the loss decreased, then it is OK. We set wait parameter to 1. If it didn't decrease, we should check two options. First, if we waited for increasing more than n steps. In this case, we should stop training. Otherwise, we increase the parameter wait, which is responsible for how many iterations we are already waiting. And that's it. Again, the only idea behind the early stopping, if our validation loss didn't increase for n steps, then we should stop our training. Finally, what should we do in practice? At first, we should always use early stopping. Always. Secondly, big networks plus regularization is better than small networks. As a regularization technique, people usually use dropout. Drop block is also good, but it is a recently proposed method which is not implemented in deep learning libraries yet. That is all for this video. Thank you for watching. Now we came to the question of speeding up our training and normalization. Training of modern convolutional neural networks may take up to several weeks, and the question is, how can we reduce this time? Of course, we can use several GPUs, but it is not always available. Moreover, training time can take several weeks even with multiple GPUs. The one way to think of speeding up our training is data normalization. If the data points will be close enough to each other in the linear space, the network will find the dependencies in the data faster. Usually, normalization is performed in the way where we make our data to be zero-centered, that is, with a zero mean and also with a standard deviation equal to 1. In order to do it, we should first pre-compute the mean and standard deviation for each feature before training. After that, we should first subtract the precomputed mean and divide by the precomputed standard deviation. Note that we add some small epsilon to our standard deviation in order to avoid division by zero. This normalization is applied before training to all data points, including train and test objects. However, we have another problem that I described to you in the section with nonlinearities in the convolutional module. If you haven't seen it, please do. It is really important to know, and many other courses avoid this information. So, we have a sigmoid nonlinearity function. What is the problem with it? It is its gradient, that is equal to 0 almost everywhere except of the small region around 0. For us, it means that when our data after some layer will not be around 0, our gradient will vanish. It will be 0. And our weights will receive no update at all. And we will learn nothing from our data. Okay, what can we do with it? In 2015, researchers proposed a new normalization technique called batch normalization. The idea behind it is simple. Let us create a layer that will normalize our data and will set the learnable mean and standard deviation to our data. So, how does it work? We again, as in standard normalization, compute mean and standard deviation. Then we subtract the mean and divide by standard deviation plus some small epsilon. After that, we multiply our normalized data to the new learnable standard deviation and add new learnable mean value. Pay attention, these parameters are learnable, which means they are also optimized with gradient descent. Also note that this is a layer which can be inserted before each linear or convolutional layer in the network. It occurred that with the batch normalization, the training time decreased by 11 times on the inception architecture, which we will study in the next module. Just imagine, inserting several batch normalization layers can speed up our training by 11 times. It's amazing. There are many other regularization techniques, such as batch normalization, like layer normalization, instance normalization, and so on. Let us compare the batch normalization with layer normalization. In case of batch normalization, the mean and standard deviation is computed for each feature separately, and we obtain the mean of a concrete feature in the batch along with the standard deviation for this concrete feature. In case of layer normalization, the mean and standard deviation are computed not for the feature separately, but for the objects. So for each object, we compute its mean and its standard deviation among all features. As a result, for each object, we will have a single mean and standard deviation. Layer normalization can be used for images, but usually people prefer to use batch normalization. Layer normalization is more popular for text processing and neural language processing. When you use batch normalization in practice, you should insert it after the convolutional layers and before nonlinearity, such as ReLU or sigmoid or any other. Of course, you can insert it in another way, for example, after nonlinearity, and sometimes it can be better. Instead of computing statistics such as mean and standard deviation for a batch, Usually people use running statistics, which is computed with the use of momentum parameter, which is available in PyTorch. So that is all for normalization. Next time we will discuss weight initialization. Thank you for watching and see you in the next video. Hello, my friend. In this video we'll talk about data augmentation, a good technique that allows you to extend your dataset and to improve your quality. So what are the problems of convolutional neural networks? They are in fact very sensitive to rotation of images. So if we have good prediction for one image and if we rotate it a little bit, the quality may decrease. It is also sensitive to light. If we trained our network only on light images and then make the images dark, then the quality again may decrease. And also there is a problem of small data sets. For example, if you have very few amount of data, so it's hard to train a neural network and obtain good quality. And the solution for this is data augmentation. The first method of augmentation is rotation. So if we have an image of cat, we can say that rotated cat is also the cat. We can rotate our training images randomly and add to our training set and also use them for training. The second method of augmentation is flipping. So we can flip our cat again, add it to train set and train our neural network. The third method is scaling. We can use the subset, the random subset of image and also again add it to the train set and train the network. We can change the contrast of our images and we can add some random noise, for example, from the normal distribution or from uniform distribution to the image and add again this image to the dataset. Now, in fact, this method can increase the size of your dataset up to several times. But now, what have we do in case of testing? So there is no one good answer. One possible solution is not to use augmentation on testing. The second possible solution is to use some linear combination of different augmentation. So we take one test image, apply contrast changing, apply scaling, apply rotation, apply blurring, and then use average of these predictions. The quality may vary from one task to another, so you should try. But believe me, the data augmentation is a very good technique that allows you to increase the size of the dataset and increase the quality a lot. Thank you for watching and see you in the next video. In this video, we'll go into talk about existing datasets that can be used for training your neural network. The first and the most popular dataset is MNIST dataset. It consists of images of size 28 to 28 and all images are grayscale and there are 10 classes from 0 to 9. Totally there are 60,000 of images of 10 classes, as I said. Note that the quality of the network should be very big on this dataset. So the accuracy of, for example, k-nearest neighbors algorithm on this dataset is 96%. So this is rather bad dataset for testing because it's very easy. For this reason, another dataset, which is called Fashion MNIST, was proposed. There are again 60,000 of images of again size 28 to 28 of 10 classes, but now there are not digits but different types of clothes. And this is rather good alternative to MNIST. At the bottom of the slide you can see the link to this dataset. And Again, all these datasets you can download with Torch Vision library. The next famous dataset that we used in our practical videos is CIFAR-10. It consists of 60,000 color images of 10 classes like airplane, automobile, bird, etc. And there are 6,000 images per class, and all of them have size 32 to 32. Another dataset which is very similar to previous one is CIFAR-100. It again consists of 60,000 images but now of 100 classes. There are 600 images per class of size 32 to 32, and you can see the classes on the slide, like fish, flowers, people, reptiles, trees, and so on. There are also a good set of big data sets. First is Tiny Images that was proposed in 2008, and it has 80 millions of images of size 32 to 32. There exists a Coltec dataset which has around 300 to 200 size images, 30,000 images. And the last one is the most popular is ImageNet, which consists of 14 millions of images of big size 256 to 256. And what I suggest you to do, if for example you have a set of cats and a set of dogs and you want to build a classifier that distinguishes cats and dogs, try to use some additional data that is labeled from these data sets. So you are able to just download ImageNet and take all cats and all dogs from there and add to your data set, and the increasing of your data set will improve your quality. That is all for this video. Thank you for watching and see you in the next. In this video we'll talk about modern convolutional architectures, and in the next one we will discuss how we can apply them in order to solve any image classification problem. The first model that was proposed in 1998 was LINET. It was designed for MNIST dataset and consisted of convolutional layers, average pooling, sigmoid and hyperbolic tangent nonlinearities, and had the input of 32 to 32 and the output was 10 classes. The next famous architecture was proposed in 2012 and consists of 60 millions of parameters, and it took up to 6 days of training to train this network on 2 GPUs. The input of this network was 224 to 224 and the output was 1000 classes, because this network was designed for ImageNet, which has 1000 classes. The next network which improved the quality of the previous one was VGG, which consists of 138 parameters, and most of these parameters was in linear layers, 123 millions. It took up to 3 weeks of training on 4 GPUs. How can we solve the problem of different scale? Look at these 3 images. On each of these image there is a dog, but the scale is different, and on the first image the dog is on the most part of the photo, and on the last image the dog taking only small part of the photo. For solving this problem, in 2014 the inception network was proposed. It consists of so-called inception modules. The naive version of inception modules is the following. We have some previous layer, the output of the previous layer, or it can be the input of the network. And the idea is simple. Let's apply convolutions with different kernel size in order to manage different possible scaling. 1-to-1 convolution, 3-to-3 convolution, 5-to-5 convolution, and also let's use max pooling. And after we use these different types of convolution, we can concatenate output of this convolution into one result. This is the naive version of inception module. In the same paper, they proposed dimension reduction with the inception module. What is it? In fact, we leave the same convolution as in naive version, but we add one-to-one convolution, which is yellow on the right image. One-to-one convolution allows us to have the same output size as an input size, but to reduce the number of filters. It means that we easily can decrease the number of parameters in 3-to-3 convolution and 5-to-5 convolution. And they found that one-to-one convolution is better to use after max pooling, but not before it. They put all these layers together and proposed what is called inception network. But what if we want to stack more layers? What if we want, for example, to use 150 layers? In fact, if you just stack 150 layers of convolutions plus some nonlinearities, you will obtain 5 problems. The first problem is CUDA out-of-memory error. This problem can be solved using multiple GPUs, and let's imagine we can get another additional resources. Then we will have 2 problems with gradients, which is vanishing gradients and exploding gradients. And we will have vanishing activations and exploding activations. The last 2 can be solved with batch normalization, as we described in the previous section. But vanishing gradients and exploding gradients are caused not only because of activations, because of nonlinearities, but also because the number of layers. And in fact, it is very hard for gradient to go through the head of the network to the tail of the network, to the input. It is hard, and usually it becomes 0 to the input. And in fact, if you just stack 150 layers, your network will not learn at all. But in 2015, people proposed so-called ResNet architecture. It consisted of 152 layers and used skip connections, also known as residual blocks. What is it? Imagine, look at the right image. Imagine you have some X image. Then we use some weight layer, which is convolutional layer. We can use it again. But at the right part, we use X and we add this X to the output of the convolution without any modification. So the formula is on the left, where F is the convolution and X is just our input. In fact, this helps a lot with building such a deep neural network, and it occurred that such a network allowed to outperform human on ImageNet dataset. That's how it looked like. In fact, here is 34-layer residual network, but in practice they use 152 layers, and we will also use it in practice. So the bottom network is VGG19, which we looked at a few slides ago, then 34-layer network without residual connections, and 34-layer network with residual connections. That is all for modern architectures. We'll look at them in details and we'll study how to use them in practice. Thank you and see you in the next video. In this video, we'll study how can we use existing trained networks in order to improve the quality of our problem that we solve. Let's imagine the following. You have a small data set of 150 airships, of photos of airships, and you want to build a classifier which classifies, for example, different types of these airships. What possible solutions can we use? First is data augmentation, and it is okay, but it will be not enough because again, we'll have too few images in our training set. we possibly can use some existing datasets, but it is also not enough, because in existing datasets, I guess there are not so much airships. There are a lot of cats, dogs, birds, etc., but not airships. Okay, can we do something else? And in fact, yes. In fact, we can use some pre-trained network. And this is called transfer learning. Imagine you have a big network that was trained on ImageNet. For example, it may be residual net, ResNet, which consists of 152 layers, which we studied in the previous video. It was trained on ImageNet, which consists of 14 millions of images and 1000 classes. Now, we trained it. Then what we can do, we can remove last few layers, last layer or last two layers, and add some new layers and train these two layers that we added on our existing small data set. And here we can of course apply the data augmentation. Look, now we need to train not the deep network, but just small one. And the amount of data that we have usually is enough to train one or two layers. But as a result, we will have a big, deep network. And usually it works because first layers of the convolutional network allows to obtain very nice features that are proper to any problem. Another possible solution is to train all the network, not just new layers. It depends on the problem, of course, and on the amount of data that you have in your training set. That is all for transfer learning. Let's look how we can use it in practice. Thank you for watching and see you in the next video. Hello, my dear friend, and welcome to the bot recognition section. In this section, we will solve practical problem of classifying different types of bots. Imagine you have a bridge over the river and you want to set the camera and you want to build an algorithm that will classify all bots that are going under the bridge. For this reason, you need to build some convolutional classifiers. For our goal, we will use the dataset that I took from Kaggle, which is the biggest machine learning competition host. You can download this data manually by the link or use Kaggle library that allows you to download datasets. So you can just install Kaggle library and then write Kaggle datasets download. It's the name of the dataset, bot types recognition, and -p means the path where to download the data. Let's import the necessary libraries. In this video, we will load the data. So now again, as in previous practical videos, we define the transformation that we will apply to all our images. Now we have not two, but three transformations. First transformation is resizing each image to the size 224 to 224. This is necessary because different images has different sizes, and usually they are big, like 1000 to 1000, and it is really hard to process such big images with neural network. And the second reason, all the images should have the same size in order to use for neural network training and prediction. Otherwise, we will have different output sizes and can't train neural network at all. The second transformation is to tensor, which transforms the image to PyTorch tensor. And the third is normalization, when we subtract mean and divide by standard deviation, making our mean equal to 0 and standard deviation equal to 1. Now, our images are located in the data folder, and if we look at it, ls./data, you will see different folders containing images. For example, cruise ship, and you can see a set of images. If we have the following data structure, we can use Torch Vision class image folder. If you look at it documentation, it requires that all your images are located in the separate folders like dog and cat. So we load the dataset by just writing Torch Vision datasets image folder and apply our transformation. After that, we should divide our dataset to the train set and test set. We can use, for this reason, torch.utils.data.randomSplit and pass dataset, train size and test size, which has just 0.7 from our dataset and 0.3 from our dataset. And after that, we can define two loaders, train loader and test loader, as we did in previous practical videos, with predefined batch size, shuffling the data, and number of processes that will load our data from memory is equal to 2. Okay, let's run this cell. The length of our dataset is 1476. It means that it is a very small dataset, and believe me, it is really hard to train any convolutional neural network on this dataset. Totally, we have 9 classes, and it means that each class will have very few sets of images. The classes are cruise ship, ferry boat, freight boat, gondola, and others. Since we have very few images in our train set, we should do something with it. And what I propose to do is to use first method is data augmentation, which we will consider in the next video, and also transfer learning. So let us use some pre-trained network that we again will consider in the next videos. Now let's visualize the data. Here you can see the set of images, and there are some different types of ships. Okay, so that's all for this video. Thank you and see you in the next video. In this video we will make data augmentation. So let's again import all our libraries. In PyTorch it is very convenient to make data augmentation. Everything we need we can define in the transformation. So what we need here. The first transform is resizing to size 224 to 224. After that, we can define some random transformation from transforms module of Torch Vision library. Let's look what available transformations do we have. Center crop color Gitten. This is not a random. Random crop, random grayscale, random horizontal flip, random resize, rotation. So this is a set of random transformations that we can apply to our images. Let's apply, for example, random rotation. If we look at its signature, then it has the main parameter degrees. And here we should write degrees equal to minus 30 to 30. It means that we will rotate randomly our image to the angle, which will be also random, from the minus 30 to 30 degrees. Now let's try to do it and visualize the result. So okay, we did it. And here you can see rotated images. All these images were rotated randomly. Now let's look what we can do more. Transforms, random horizontal flip. Let's add random horizontal flip and transforms random vertical flip. And let's look at the result. Load again the dataset, run all cells, and here you can see horizontal flip. No, it's vertical flip. Again vertical flip, and some of them are flipped horizontally. Good. Now let's look what we can do more. Transforms dot random grayscale. So now you can see that some random images become grayscale. And in fact, this is all for data augmentation. So it is really easy to apply it, and you should always apply it in practice when you have, not only when you have small amount of data, but even when you have big amount of data. Use data augmentation. It is really easy. Thank you for watching and see you in the next video. In the previous video, we studied how to make data augmentation in PyTorch. In this video, we will learn how we can reuse existing pre-trained neural networks like AlexNet, ResNet, or any other. So let's do it. First thing that we need to do is to import Torch Vision library. After that, we have to create the network. Torch Vision dot models dot ResNet 18, for example. It's the shortest version of ResNet. And there is one parameter which is called pre-trained. By default it is false. Let's set it to true. Pre-trained equal to 2, and this will be our network. Okay, let's look at it. This is it. In fact, we just loaded the ResNet 18 and it is pre-trained. It already has trained weights. In order to look at the network in PyTorch, we can just type net. And here it is. Here we have all the layers. And now what we should do? You can see that this is sequential basic block conv2d, batch norm, conv2d, and so on. And at the end it has average pooling plus fully connected layer. What we need now is to cut this fully connected layer off and then add new fully connected layer. And after that, train this one fully connected layer using our bot's dataset. Turn off all the gradients of our network. We need this because we don't want to train again all these 18 layers before fully connected layer. For this reason, let's do the following. For param in net.parameters, param.requires grad equal to false. Here is it. Okay, we turned off the updating of all the layers. Now we want to set the following. Fully connected, net.fullyConnected fc is equal to nn.linear, and the input neurons will be 512 and the output neurons will be 9, because now we have 9 classes. Good. Now we can check our net again. So we see it has a lot of convolutional, batch norms, and so on. And the last layer is linear, 512 features, and the out number of features is 9. We have 9 classes. Good. Let's check the output shape. We have an error because we didn't move our network to CUDA. Let's do it. Net is equal to net.CUDA. Okay, good. The output of our network is 16 to 9. 16 is the batch size and 9 is the number of output neurons, which is equal to the number of output classes. Let's load the criterion and optimizer. And now we have two functions. First of them is getting quality on the test set, and the second one is training function. It gets the net as a parameter and number of epochs for training. So let's train our network for 5 epochs and look at the quality. So our training was finished and the final accuracy on test images is 70%, which I think rather good, taking into account the fact that we have only 1,500 images. Thank you for watching and see you in the next video.